So welcome back everyone to this second session. We are now in the second plenary session. Our next speaker is Dr. Ziad Haddad, who is the supervisor of the Radar Science Group in the Radar Science and Engineering section at JPL, the Jet Propulsion Laboratory, which is part of Caltech and is funded by NASA. Dr. Haddad was the one who designed, implemented, and validated the Tropical Rainfall Measuring Mission Combined Radar Radiometer, and he also designed the data compression algorithm for the Cassini mission's synthetic aperture radar. He also did something that you may be familiar with. He did this mosaic filtering algorithm to try to minimize the uncertainty in the topographic heights estimated by the shuttle radar topography mission. He also assisted the Phoenix landing radar Tiger team in developing a real processing procedure adapted to the constraints of the radar, and designed a novel data filtering application for estimating parameters in the tidal motions of Europa, which is a satellite of Jupiter, from future interferometric radar measurements. In addition to his work at JPL, he has been working there since 1991. Ziad is currently a visiting scientist at UCLA in the Joint Institute for Regional Earth Science and Engineering. So, Dr. Haddad, thank you very much for coming. Please.
Thank you. Thank you for this opportunity to share what we're doing with remote sensing, and in the context of, well, we're not doing anything right now in the context of renewable energy, but we would like to, because of some policy changes that are happening within the space agencies, not just in the United States, but around the world. So I thought I would first list what I think are the main areas where remote sensing, observation specifically, not just remote, but from space, can help with energy, either generation or management. And but before, this is not on the slide, I just want to explain why it is very interesting for me in particular. We just had a meeting in Washington where the subject of the meeting was the applications of a new constellation of satellites with different instruments, what the applications were going to be. And the constellation of satellites is designed, mostly, to measure precipitation, rain. And the two main classes of applications that were mentioned were weather forecasting and drought monitoring and prevention. And all the discussions, there were presentations by individual scientists and researchers, some operational people, and there were breakout sessions where people get together and try to say, well, you know, this is how we could do this better and whatever, and then they make a report. But the most interesting thing for me was that we were always thinking in terms of major events, preventing disasters, monitoring disasters, forecasting. So, for example, hurricanes. Can we better predict how strong they would be? Can we better forecast where they're going to go? For drought, it's the same thing. The main way in which we saw our observations as being helpful was in preventing people from dying or from having a huge effect on their lives. And it was just so uniform. Everybody who was speaking was always thinking in terms of major disasters or big hazards or major events. You know, can we tell if there's going to be more storms or not? And it just seemed to me like we're missing a huge part of this application area that would be of benefit to the application people, but also of benefit to us. And that big area, it's not because I come from, America, but it is, the very capitalistic portion where, the observations could be helping people make more money. Just as simple as that. Helping a company be more efficient about whether the water that they're getting should be spent on irrigation tomorrow, or whether they should sell it to somebody else because they're not going to need it because tomorrow it's going to rain exactly in the area where they would have irrigated, for example. Or if it's not irrigation, if it's wind, should they be storing the energy that they're going to be generating tomorrow or buy more energy for different locations? In other words, just day-to-day management that would probably not cause anybody to stay alive, that, instead of dying, or it wouldn't have dire consequences from what we usually think of as socioeconomic impacts. But it could have a huge effect on the bottom line of the company who is managing the energy. And, of course, it could be of great use to people who trade, either in the energy or in the grain, the corn that's used to produce ethanol, or et cetera, et cetera. So with that in mind, it seemed to me like we've never quantified how much the observations that we are making, with satellites, what effect they have quantitatively on the bottom line of the companies, of the traders, these are not effects that can be quantified easily. And even though you're going to see equations, and I have some animations and all this stuff, so it's going to sound kind of scientific, but I was pretty careful to try to include only the equations that are actually important to be able to allow us to quantify the effects. How big of an impact would this observation have on the ability of this company to, or it doesn't have to be a company, it could be government, to manage these resources. So which resources would we be talking about? I have a list here. The pointer works? Yes. So I just put 4 items, which I think is already a very good list to start with. Photovoltaic, wind, surface wind, near surface wind, 10 meters, 80 meters, you pick, ocean waves, and biofuels. In each one of the cases, the area in which observations can help is slightly different. In the case of photovoltaic, what you're really interested in is being able to forecast the solar irradiance in order, to be able to manage the production better, but also the estimation. In other words, not just looking in the future, but to be able to diagnose in order to pick an area in which you would want to deploy whatever assets you're going to deploy, photovoltaic cells. In the case of wind, very similar. You either want to historically know what's been happening in a given region, or around the globe if you want to be comparing different regions, and you also would like to forecast. For biofuels, it's a little bit different because if you're trying to monitor a plant and make decisions about when you should harvest, when you should hire people to do the harvest, is your competition going to have as good of a yield this year as you, or is the demand going to be great in some part of the globe because their crops won't produce as much? You would need something that I refer to as monitoring, because it's not just a question of making an estimate. You really need to be able to accumulate things in time. And you'll see, I'll have some more specifics about this. But whichever one of those 4, you're talking about, the application that I would like to keep in mind is supply or demand management and the resource yield management. So let's see how your input can be crucial. So let me explain a little bit more about the remote sensing part. What is it that we measure? How do we measure it? And specifically, I'm going to concentrate mostly on the forecasting because that's the part that maybe is not very well appreciated. So I went over this, we're not going to go over it again. How does forecasting work? I tried to put a diagram that explains in a simplified fashion what goes into a forecast? You start, right now, the present is right here at 9 p.m. I'm just picking a time. And you are trying to forecast for the next periods what's going to happen to the variables that you are interested in. And since we might as well, because this is the running example that I have and we'll come back to, let's assume that we're talking about atmospheric variables. So we're looking at predicting temperature, pressure, wind in 3 dimensions. So it's not just wind at the surface, not just temperature at the surface, not the skin temperature. I mean, it is that, but it's also everything else in 3 dimensions over a region that could be the whole globe, but it could also be regional. I'll get back to the distinctions in the domain size in a little bit, but to explain how the forecasting works, it works in 3 steps, and I color-coded them. First, what you'd like to do is to generate what I'll refer to as model-only trajectories. So you have a dynamical model. We have a dynamical model. We have many dynamical models. What the dynamical models do are they start at a point in time with values for temperature, pressure, the prognostic variables of the atmosphere in your 3-dimensional domain. And I symbolize this just to be very simple here in just 1 dimension. This is actually not a single dimension. It's many, many, many dimensions. But take one variable at one point in time, at one location, surface pressure, for example, and that's what this is supposed to represent. In reality, as I said, this vertical axis is huge. It's like 10 to the 9 is a typical dimension. And you start, doesn't have to be a day earlier, usually it could be a little bit earlier than a day earlier, but you spin up your model, so you start to run your model. What the model does is it takes these variables at the initial time, right here, so in this case 9 hours before, before the present, and it starts calculating their evolution into the future, 1 time step at a time, and you get these yellow trajectories. So the surface pressure could either, stay fairly constant and then all of a sudden increase, or it could have a dip. This is supposed to be the mean of all the possibilities. So you generate a model only. So this is just the model is trying to solve the equations that govern how these variables interact in the atmosphere. You have to conserve matter, you have to conserve energy, you have to have continuity of fluxes. These are simple equations that you write down, not that simple. Anyway, they're not that complicated. And you just solve them, parabolic, 1 time step at a time. So you select your time step. And if you start at 9 o'clock in the morning, by 9 o'clock in the evening, you will have this trajectory of all the possible evolutions that the model says are possible if we only consider the model. Now, at a couple of points in time, we will have some observations. So the model has done things based just on the model, and now a satellite goes by and measures something. What the satellite measures is hardly ever one of your variables. It's hardly ever the case, for example, one of the variables is rain. We do not have satellites with instruments that can just look down and measure rain. They'll measure something like the brightness temperature at 19 gigahertz over this particular area, and over the next area, and over the next one. And so you get a map with 19 gigahertz brightness temperatures. And the brightness temperatures, so now there's some physics that relate them to what the rain is. It's the same thing with many of these, well, just about all the variables in the model. You hardly ever measure directly a variable from the model. But I'll get back to this point in a little bit. So the challenge now for the forecast, you don't want to just be running the model all by itself, because the model is like, some person sitting somewhere, looking at a crystal ball and then telling you things about the future. Sometimes they're believable, sometimes they're not. It works better with coffee grinds, but, the point is, as long as it's just a model, it's not as good. I mean, why did we get these observations for? So the challenge is to be able to reconcile the two at 9 p.m. You come to the point where you want to reconcile the observation that you got with what the model was saying. And it's almost always the case that the observations are not quite consistent with what the model said. So now you have to do something. And there are several things that can be done. One of the things that can be done, and that many people do not very well, is to take the observations, try to invert them, So you have an observation of the brightness temperature that's supposed to be related to rain. Well, figure out what the rain should have been, and then look at the model, look at what the rain in the model was, take it out, and put that value that was observed in the model. That's sort of self-defeating. Not sort of, it's very self-defeating. This model, you've spent a lot of energy and time and money trying to make it so that it's all consistent with all the physics, and then, you know, as soon as you have an observation, you're just going to go in there, break it, take something out, put something back in. It's not, you know, it's not just that it's not elegant, it's intellectual, it's not consistent. It's like, you know, you will not be conserving mass, you will not be conserving all the things that we've spent centuries trying to figure out how that works. So that's the first, you know, big problem with the notion of just replacing things. And the other big problem is that in order to be able to interpret the observations correctly, as I was saying before, you don't just observe temperature, you don't ever observe pressure, or, you observe something that is related to these things. And in order to be able to convert an observation into one of the variables, something useful like an observation of rain, if you want to convert that into an estimate of the actual rain, you have to make many assumptions. You do. You have to make an assumption about what the background emissivity was. You have to make a background about different absorption coefficients in the atmosphere. And these assumptions that you have to make may not be consistent with the model. So in other words, the model can help interpret the observations just as much as the observations can help improve the model. It works both ways. So you have to do something to go from the yellow, to be able to incorporate into the yellow, into the realm of possibilities, the observations, to reconcile the model only, that was yellow, with what the observations said. And once you've done that, and I'll explain how that's done a little bit better than I just did, then you want to do the forecast for tomorrow, and that's the blue. And that's relatively easy at this stage, because to go from 9 p.m. forward, you do exactly the same thing as you did at 9 a.m., except that now you're starting not with these somewhat unknown variables, but now you know them better, because you know them from what the model said they could be, adjusted by what the observation said they really ought to be. So that's the blue part. Okay, so that's how the forecasting works. Well, that is the question, isn't it? Does it really work? I mean, as you all know from reading in the paper what the weather was, or now you look it up on an iPhone, whatever, you know, sometimes they tell you that something and it happens, and sometimes they tell you something and it doesn't happen. So in the context of energy, let's skip, because otherwise I'll never be able to make the whole thing. Well, maybe I shouldn't skip. I'll explain how it works. This tells you a little bit more about the dimensions. I mean, you know, is this something that one can do at home, or is it something that requires a huge amount of computing power with big computers, or is it somewhere in between? Well, basically what the models do is they split up the atmosphere, or the ocean, if it was the case of the ocean, into several vertical levels, usually on the order of 40, could be a little bit bigger. Horizontally, you also need to have fairly fine sampling. So for a good regional model, you'll have at least 500 points this way by 500 points that way. So this is horizontal on the ground, this is vertical. And so in each one of those boxes that represent, each box represents a volume element of your whole domain, you represent all the variables that you have. Different models have different representations, but usually you will have on the order of about 12 or less, but you know, hardly ever more, because you really need the temperature, that's T, the pressure, the three components of the motion. The air is never still, it moves, and that's very important because, as we'll see. And then water vapor and the different phases of water. The reason why we don't track other things than water is because of the latent heating. Water vapor is the most abundant greenhouse gas, and whenever it changes from liquid to solid to vapor, in any one of those directions, heat, there's quite a bit of heat that's exchanged. In fact, there's a huge amount of heat that's exchanged. The amount of latent heating that comes from the changes, the phase changes of water, explains between 2/3 and 3/4 of all the energy that drives our weather all around the globe. It's, you know, 3 times more than the sun. And so it's crucial to be able to accurately represent the phase changes of water. And as we'll see, that is still the main challenge of this whole enterprise, the whole modeling and forecasting enterprises. The phase changes of water are still, to this day, sometimes they work and sometimes they don't, and they are the main reason why we don't get very good results. In any case, when you put it all together, it turns out that the number of variables in any one particular column over any one horizontal points, well, there's 40 of them times 12, so you have about 480 variables over every column, and then you have to multiply that by 500 times 500 to get an order of the size of the domain that you're looking at. You're looking at 120 million variables at a time, at any point in time. And that's what you have to keep moving every point in time by solving whatever the equations until the moment when you do make an observation. So this is supposed to represent the equations that govern the dynamics and the thermodynamics of the system. Then you make an observation, which, as I was saying before, is never the variables directly, but it's some function of the variables, and this function h is almost always nonlinear. And so what you'd like is to be able to figure out how to reconcile the two. Okay? And once you've reconciled them, then you can propagate forward in time, and that is the forecast. So one of the main things, of course, that I haven't told you is, what are these observations? How many do we actually currently have, and where do they come from? Well, we make, and when I say we, I'm talking about all the space agencies in the world. There are some private companies that are doing things now, but nowhere near the levels that the European Space Agency, the Indian Space Agency, the Japanese Space Agency, the UN, of course, NASA and NOAA in the United States. We make about 2 billion observations every day, putting all of these together. And it doesn't, I don't need to say whether, how many of these observations are actually from satellites and how many are from, say, surface stations, because, it turns out 99.9% are from satellites, most of them. And the models that make routine use of this right now, that are used every day operationally, there's 5 big ones. And I've listed them here. There's the model from the European Center for Medium-Range Weather Forecasting. And those are, the reason I put it first is because usually its forecasts are pretty much the best. However, when I say the best, this is part of the problem, is they're the best on average, depending on what your use is. It's not very useful for you if the ECMWF model forecasts the temperature very well, if in fact what you are interested in is surface rain, for example. And I can tell you right now that none of them do surface rain extremely well. But anyway, ECMWF on average does the best job. The horizontal resolution, if we go back, I mentioned that we have, you have to discretize the grid on the ground. So how big are these boxes here? Well, so the ECMWF boxes today are 16 kilometers big. What that means is that the assumption is that over these 16 kilometers, things are pretty much uniform. There is a little bit of a fudge factor, but otherwise we're not going to try to resolve things that are better than, well, they're not going to try to resolve things that are better than 16 kilometers. However, they do already have plans and a path to get to those, to realize those plans, so that by 2025 they will have a 2.5 kilometer grid globally. And the forecast that they make, I kept the forecasts in blue because that was the third step, they make forecasts out to 10 days. That's why it's called medium-range forecasting. You can obtain from them, I'm not saying it's always going to be very accurate, but you can obtain from them a forecast for all the prognostics, and some diagnostic variables of the atmosphere out to 10 days. Now, in the US, we have 2 agencies that are involved in this numerical weather prediction, NASA and NOAA. NOAA is the operational agency. It stands for Ocean and Atmosphere. NASA is air and space, so anyway. NOAA has a model that's called the GFS, Global Forecast System, and its resolution is a little bit worse than the ECMWF, but it goes out further. And I'm mentioning a second one because this one is not global, it's more restricted to North America, and I will talk about the difference between having a regional model as opposed to the global one. Anyway, the first ECMWF, second is NOAA, and then Canada, the Naval Research Lab, and the United Kingdom, the UK Met Office also has a model. They're all, have comparable forecast ranges and comparable resolutions. Of course, they do assimilate, as I was saying, observations from instruments that are not on satellites, radiosondes and aircraft measurements and some surface weather, but by far the greatest number of observations are the ones that come from satellites. And I'm not going to go down the list here because I have it ranked. In a little bit I'll show you what these produce and how important they are. Not all these observations contribute equally to making a good forecast. But before we do this, I wanted to talk about, so this is the global models, and they assimilate all these satellite observations. In addition to this, I'll have two other examples that I would like to talk about. One of them is a regional model that's called High Resolution Rapid Refresh, and that one is regional. The model itself has 3 grids. So one grid that is very coarse, but big, the blue one, and its resolution is 13 kilometers. Then another grid where the resolution gets better, and a third grid, the green one, which is 3 kilometer resolution. And so within this green grid, every 3 kilometers, it will produce an estimate, a forecast, every hour. And it does this, so hourly, out to 15 hours, so you get a little over a half a day's worth of forecast from it. And they don't assimilate, of course, in these models, the models, because they take a lot longer to run. The main difference between this and all the global models is that these regional models can actually correctly represent the dynamics of the changes of water. In the bigger models, it would take way too long to be able to produce a forecast, so the dynamics of water are not entirely, but they're mostly parameterized. What that means is they're not explicitly, the equations that govern them are not explicitly represented. So because these models are more, have more it's not accuracy, it's have more precision in them, and so therefore they take more resources to run, they cannot assimilate as much because assimilating the observations takes quite a bit of resources itself. So they assimilate a few, less things. One of the main, most important things that they do assume from the satellite observations, one of the observations that they do assume from the satellite is something called the motion fields, the atmospheric motion fields. And what those are is we have a few satellites that are very far from Earth in geostationary orbit. Most of the satellites are in low Earth orbit, so they're about 400, 500, up to 800 kilometers from the surface, and they just orbit with a very myopic view. They're so close. Doesn't sound like 400 to 800 kilometers is close, but they are close. So close that they don't really see very much at a time. And then we've got a few that are in geostationary, which is 37,000 kilometers away. Not 400, 800, it's 37,000. And there you get a global view of just half the planet at a time, almost. The edges aren't quite done very well. And the motion fields that you get from those ones, so the only instruments that we have are on those geostationary ones, the ones that are far away, are cameras. They're visible. They usually have, let's say 5 channels. So visible, a couple of infrared, and something between the visible and the infrared. And basically they're just measuring a temperature in whatever band they're looking at. And the reason we don't have fancier instruments is because fancier instruments would have to be bigger in order to get a good resolution from that far away, and that makes it very, very expensive, because to launch something and put it that far away is very expensive. And they then take consecutive images and see how, just like you've seen on TV, the clouds have moved from one image to the next. And by subtracting the temperatures from one image and the previous image, you can figure out which way each cloud has moved and create a motion field out of this. And it turns out that's one of the observations that is the most useful to be able to represent. It turns out it's one of the most useful ones. It is very useful, but it's not sufficient. Anyway, that's what the second example, so we had the global models. This is one of the regional models, that's another example. the motion fields are important, one of the most important observations that it does assimilate. And the third example that I wanted to talk about is the example that many individual research groups have done. This one in particular is very applicable to energy. And it's an application from the University of California at San Diego. Again, the model has 3 grids, the innermost one centered around San Diego, and they want to also assimilate the GOES cloud top temperatures, the temperatures that I was telling you about from geostationary, except what they want to do with them, this is specifically done for solar irradiance. So for photovoltaic power generation, they would like to predict the cloudiness over that portion of Southern California, which is prone to these low-level clouds that can come in the morning and then dissipate by afternoon, but sometimes they don't materialize, and they make it very difficult to manage the power generation. So how can one evaluate the impact? So in this case, they have the model. The model by itself doesn't do a very good job. Now they do know that they have some observations from satellites. How do you quantify whether the observation did, solve the problem for you and what value it added? In this case, the previous example, you've got a few more. The point soundings, it's just a point. It's not going to make a huge difference, so let's not worry about it too much. But there are a few all these 3 here are satellite observations. How do you quantify how important they were? How do you quantify if they helped you either forecast or estimate what was happening before? So in the case of the very first example, they've already done this in a certain sense, on average. In the case of the global models, this is a list of all the satellites that we have. And for each satellite, what you see on the right is the forecast error contribution. How much each one of these has helped you or has helped them in producing an accurate forecast. And the funny thing that you see is that what I had said before about those, so these are, where it says here GOES winds and Meteosat winds, those are the motion vectors that are generated from the geostationary satellites, the faraway satellites that take pictures of clouds and compare 2 consecutive pictures in order to decide where the cloud has moved. GOES refers to the American satellites and Meteosat as the European satellites. And if you look closely, you'll see that you have to go pretty far down the list before you see the Japanese geostationary satellite. And its contribution to the accuracy of the forecast is not very high. It's certainly not as high as GOES and Meteosat. And of course, neither one of them, not any one of those 3, is as high as the one that by far takes the prize, and that's these ones are following behind. These are the humidity sounders. And this is a humidity sounder, this is also a humidity sounder, these are the sounders. And the reason why this one is a lot better, has a higher score than either one of those 2, is that right now we have 4 of them, 4 of these satellites going around, whereas there's only 1 YASI and there's only 1 AIRS. And as I said, this is just a quantification of the average improvement that the observations do for the forecast. I was going to explain a little bit about why these ones score poorly. These 2 don't score too badly. The reason why they're probably not higher up, because there's certainly a lot more of them. There's only 2 GOES that are operational and 2 Meteosats that are producing the winds that are going in here, but their effect is much bigger because they take data over the whole half globe every 15 minutes, as opposed to these ones which just come by whenever they come by. So the data that comes out of these is more numerous. There's a lot more observations more frequently. But the observation is not as specific. It's unfortunate. As you can imagine, it's only telling you what the temperature is at the top of the cloud, and then it's telling you what the temperature is at the next 15-minute interval at the top of the cloud, challenging you to try to figure out, if the cloud has now become cooler, which means that it's higher, or if it has become warmer, which means it has receded down, where are you going to attribute this motion to, which level? So interpreting them is not without a challenge. And the reason why the GOES and the Meteosat do a lot better than the Japanese, there's nothing wrong with the Japanese technology. It's just that the Japanese geostationary measures over the Pacific, as opposed to these other 2 that measure over pretty much the Atlantic. Over the Pacific, most of the clouds are high up, And so the motion is mostly interpreted as a high altitude motion, which isn't necessarily what affects the models the most. The models really would like to have some observations of what's happening closer to, the lower troposphere, the boundary layer, because that's where it matters most. And you don't get that very much just by the nature of the climate that governs the Western Pacific. Over Japan, we usually have much taller clouds, a lot more convection, and that explains. This is all very simplified, but that is my point, is that so far all of these things are averaged, percent contribution. Well, I didn't put average because it is also average. These are all fairly general statements that don't go to the heart of the problem. So let's go to the heart of the problem before the time runs out. And so here I discussed that global example. So let's go back now to the third example that I had told you about, which is the San Diego one with the 3 nests, and we're trying to produce an estimate of the solar irradiance. What they do in order what everybody does in order to produce the forecast, it's that reconciliation step here, going from the yellow to the green. That's difficult. Well, what is done is you start out with what the model has calculated, that's called background, XB, and you know what you've measured, that's O. Yep. And what you're looking for now is something that I'm calling X underline, that is between XB and whatever much it takes to produce O. So the assumption that's almost always the case is that what the model calculated, XB, is not good enough. If I were to take XB and calculate from it H of XB, which in theory should give me the observation, it won't give me exactly the observation. There'll be a discrepancy. This quantity here will not be 0. If it was 0, then I don't have to reconcile anything. The model got it right, but I didn't need the observation. That's almost never the case. So if it is never the case, that means that I have to modify XB somehow. I have to produce my new value for the model, which I will then take forward with my forecast. But this new value has to be close enough to the old, the one from the model, and it has to be such that it's close enough to the observation too. That's the process of reconciliation. Because this H is very nonlinear. This isn't like, I just divide by H and we're done. It's a very nonlinear function. The first thing that has to be done, well, that they do, and that most people do even today, is to somehow simplify it so that you do some linearization. And that is the crucial step that is very difficult to do and usually does not produce, well, up until today, does not produce a very good answer. So you go from the equation that we had originally, the exact equation, to an equation where now I have X and it's all linear in X. This is my unknown. This is the step that has to be improved later. But I just wanted to show you an example of how this is done. If I'm solving this problem, I want to minimize this expression. It's all linear. Not only is it linear, but it's a quadratic in X. Now that's a much easier thing. Finding the minimum or the maximum of a quadratic expression, x squared plus 2x plus 5. We all know how to do this. Well, in theory. And in many dimensions, it's not that hard, and I'm just giving you the solution, just work it out. It turns out you have an exact, nice closed form for the solution. All you have to do is you take your background, you take something that I'm calling H prime, which is the sort of what's allowing you to linearize your observation, and then you sort of do a weighted average of them. It is that simple. It is that simple, but it's not as accurate as solving the full problem, the full nonlinear problem. I have to linearize to do this. And in their case, this going from O on the left to the H prime goes as follows. What they're observing are the cloud tops. I'm not showing the exact value of the cloud tops. I'm just showing wherever there is a cloud, I'm showing it with green. And as you can see, usually the clouds that we have are of a marine origin. You've got this marine layer and a lot of condensation here, but you also have some clouds inland. And what they do is that they convert this into an adjustment to the water vapor. So that's their H prime. They take the values that they have observed from the cloud temperatures, and from them they decide wherever I have a cloud, that probably means that the model should have had more water vapor, so you have a positive adjustment. And wherever I don't have a cloud, that's also an observation. I observed that there was nothing, and that means that I should have less, a negative adjustment. I should have less water vapor. And then it is this adjusted observation that gets assimilated into the model. And when they do this, here's what they get as far as the insolation. So now we're looking at the difference in the horizontal solar irradiance. Horizontal just means that if you have to assume that you've got a flat plane. So assume that, it's a flat photovoltaic cell, and you calculate the irradiance over that. There are calculations here. What you see on the top is what the global model produced without any observation. The difference, between that, this is NAM minus the validation estimates. And the validation estimates are in situ measurements that are calculated. So this is supposed to be the truth. So on this line, we have, as a function of the local time, 7 o'clock, 9 o'clock, 10 o'clock, 12 o'clock, we've got the difference between the model with no observation and the exact measurements, in situ measurements. And down below, we've got the difference between the forecast and the estimates. And you can see that by assimilating this fairly simple transform of the observation of the cloud top temperatures, the model did better. The forecast comes out better. It does not come out perfect. You still have areas of red where it counts, because this is where you want to do the photovoltaic generation. You're not interested in putting these things floating out on the water. And of course, the other thing that you could criticize is that by 12 o'clock, they're doing just as well or as poorly as one another. So, it is an improvement, but it doesn't solve the problem. But it is an example of how the observations are useful and how you can quantify exactly how useful they are. So that's one. This is from that intermediate model that I had showed you, where we were looking at the entire United States at a 3-kilometer resolution every hour out to 15 hours. This is the way they're using it right now, is actually not so much for a forecast, but rather for a diagnostic. If somebody is interested in figuring out the exact history of a whole region to try to decide exactly where they want to put their wind turbines, well, how are you going to decide that? It's very, very difficult to actually directly measure what the wind would be at a 3-kilometer resolution for the whole of the United States. They can. This isn't a measurement. It is a forecast, which I have averaged here from January 2012 to May 2012. But over that whole period, what you're seeing here, this is what the data assimilation has allowed you to do. You can see the average wind over the different areas, showing you exactly these corridors where you do have very high wind. And as it turns out, it's also the places where the percentage of time that the wind is above 12 knots is also very high. They don't always exactly coincide. But the point is that you can generate these very high resolution maps only thanks to this kind of blending of observations and the model. Now, the observations are not of the wind. We don't have observations of the wind at this kind of resolution over the whole United States. They're observations of the temperature and the pressure and the humidity. They help you improve the whole model forecast, which, when you then average it over the 5 months, produces this kind of map that would be very difficult to produce any other way. However, it's not without problems too. What you're seeing here is the actual diurnal. So what I showed you was an average over all the months. And what you're seeing here are a map. On the left is the diurnal cycle of the rain that's produced by the exact same system. I mean, if the system isn't producing all the variables correctly, well, chances are maybe some of them are not being produced as correctly as others. And it's cloud estimates, so the wind estimates seem to be fine, but the cloudiness estimates, in this case I called it rain, but it's both rain and cloud, don't compare extremely well with what the ground radar sees. The ground radar composite map is on the right. The whole data assimilation forecast is on the left. I have again averaged it over the 5 months period, but this time 1 hour at a time. So I averaged all the 1 o'clock ones and produced one slide. I've averaged all the 2 o'clock ones, and so what you're seeing is the repeat of the cycle. If you're actually interested in a specific time, all you have to do is you look at here, this is the GMT time, and I tried to synchronize them so that they're producing the same thing. As you can see, the general patterns are not too different, but they're far from being similar. In particular, Florida, I mean, it just gets it not not right. And there isn't any excuse for not getting Florida right. Why? Because you see, the ground radar has a problem over the mountains. All this region here, it's the Rocky Mountains, the Cordillera, and there's blockages, there's ground clutter. So the fact that on the right, what's supposed to be the truth tells you there's nothing, it's all white, does not mean that it should be all white. This is not necessarily wrong. But here, this is probably one of the flattest parts of the United States. There is no excuse for getting rain or cloudiness when the ground radar says there isn't any. So they're not without their problems. This is to illustrate the problems with the ground measurements. And so how do we treat the nonlinearity? Well, one of the problems was the passage between what I was telling you before, from the real problem, which is this one, where H is very nonlinear, to this problem where, you know, you've kind of tried to linearize it away. And one of the things that, the reason why this isn't right, is it going to work? It is going to work. Is that, you know, condensed water forms, there's condensation that happens and evaporation. There's sources and sinks. It's not just a question of moving the clouds around. So as long as your model does not really take this into account, does not know, it may try to simulate what's happening, but if it is not actually doing the condensation, the changes of phases of water correctly, if all it's doing is taking the motion fields, like the cloud was here and it moved there, and trying to assimilate just the motion observation, the horizontal motion observation, it's not going to get it right. Why? I mean, look at what's happening here. The cloud, this cloud, well, you know, that went away now. We had a few before that were there is a portion of the cloud that advects. It's called advection, the horizontal movement. But most of it, what's actually happened with the cloud isn't that the cloud just moves horizontally. It's the cloud, as you can see, forms. I mean, you all of a sudden get condensation where there was nothing but water vapor before, and vice versa. I mean, there are some areas. Look at this one, for example. This is a good one. There is some horizontal motion that you can detect, but a lot of the motion comes from the sources and the sinks. And if you don't represent that correctly, it'll be very difficult for you. So how can we generate that? How can we model that correctly? That's extremely challenging so far because we do not ever have any observations directly of the process of condensation and evaporation. It's very difficult to put something out there in the atmosphere and wait for water to condense, and then you make your measurements and try to see how they correlate with every one of your other variables. What we do have, though, are these sequences that I was telling you about, and I'm showing you one of them here. This is from a ground radar, not from a geostationary radar, and this is a blizzard that happened. This is California. This is the coast of California. If you follow it right here, it's not very easy to see. We have our own Cordillera, and there it is. And then we have some mountain ranges here on the coasts. The relief is shown. And this is a blizzard that happened in January. God knows we don't have that many of them over there, but so, you know, with very strong features in it. And the idea here is to try to exploit this observation, not just to look at the motion. In fact, you want to take the motion out. What you're trying to see is how much water has condensed and how much has evaporated. In other words, if I could take two consecutive images and take the motion out, bring this line back to where this line was, bring it a little bit, it doesn't move very much. The pictures are 5 minutes apart. But it's still, they have moved. You can tell that this picture is not exactly the same as this one. This arm here doesn't look quite the same as this one. There's been a slight. If I move them back and then subtract them, I don't want to know the motion. I mean, I have to know it in order to subtract it, but I want to take it out. And then what I want to see is, with what's left, how much of this red got redder and how much of it got bluer. Did I get more condensation or more evaporation? That's going to tell me how much, where the sources and sinks are, and that's going to allow me to get a better representation in the model of this phenomenon. And when we do this, that's the image on the right is what you see. You see a completely different structure from the one that we started with. I may have broken the machine. It's trying hard to accommodate. Yes, good. So now we have them all in sync. So on the left, we still have the same observations, and what you're seeing on the right is this exact same storm, but now I have subtracted the motion. And so what you're seeing are these things that are sort of organized parallel to the coast and moving inland much better than what you see here. When you look at it, you'd think the one on the left, on the right has nothing to do with the one on the left, but it is. This one comes from the other one. And maybe you'll see it better on the next slide, which shows, let's go to the third one, because those show a little bit better, you know, what the organization, what is it that these sources of sinks are doing. You see that most of the red, which is where the sources are, is concentrated near the coast. And most of the blue, which is where the water comes out of the system, so red is where the condensed water comes in, and blue is where the water comes out. The blue is mostly over the mountains, inland. And what it's showing is exactly an observation of how this water vapor that's coming from Hawaii, it turns out, as you see on the future slides, hits the coastal mountains that force it to condense because of the orography, so you generate the condensation right there, and as it moves inland, it precipitates out and evaporates back out too from the top. So we do have some new ways of interpreting the observations from space to give us these pieces that we have been missing so far in getting the irradiance correctly, getting the clouds correctly. So far we've only applied it to cases that are very intense because, well, if we don't get it right there, then we probably won't get it right anywhere. And the next thing that I wanted to talk about is the second problem, which is to account for the nonlinearity. So the previous one was to account for the sources and sinks, and now how do you account for the nonlinearity? And you know what? We don't have any more time, so I'll just skip that. This was a hurricane, and it's an interest. If somebody is interested, I can show you later. But let me get to the almost last slide. So this summarizes why it is that we are doing everything. Why I'm doing all of this is, as I was saying before, the space agency priorities are changing. And in fact, one of the space agencies, starting in March, at the end of March, the fiscal year in Japan ends at the end of March, are going to change their, the way that they decide whether missions should be pursued and money should be spent on them or no. First of all, they have a new office of National Space Policy. It's no longer going to be the space agency that's going to set space policy. There is a specific office. And I'm just going to read this because it's pretty shocking to me anyway, that based on the latest 5-year basic plan for space that was promulgated by the Office of National Space Policy, the new direction is putting pressure on JAXA to cut, postpone, or reduce, actually it should be and, some or most of the agency's flagship science, technology, and manned spaceflight programs. Why? Because the first order of business for the new JAXA is to reorient the nation's space program to activities that may produce some commercial return. So I think it's vital for the people who do produce remote sensing measurements from satellite to show that they are already useful for the commercial return. In particular, for the people who are interested in energy, because it's the observations are directly useful for making, estimates and making forecasts of cloudiness, wind, and the conditions for biofuels. So what's missing is the quantitative, and I promise you this is the last equation, it's the last slide, is the quantitative estimate of how much your forecast, which I called XF, it's whatever's produced at the end of the forecast, is sensitive to the observation. We have the tools to do this. We know how to calculate just about every part of the equation. What we really don't know yet is what case to apply it to make the calculation. We can calculate how sensitive the actual, any one of the variables is, any final variable is, to any one of the observations. It will depend on how we're modeling the observations and how we can better model them. It will depend on, well, everything that it should depend on. This is the chain rule. But what we still need to do is identify some cases where it would be indeed interesting to predict, to forecast either the, I thought I had this here. Yeah, I guess I didn't. Either the amount either the accumulated temperature deficit, accumulated rain. So there's several candidates for what this XF could be depending on the application. I guess I'm done.